order to measure the MTF, we had to have a setup done. So most of this was already set up for us when we got here, but just a quick run through. We've got a laser, an objective with a spatial filter to clean up the beam, a collimation lens to expand it, so that way we have the full beam expander, a mirror to bend the light by 90 degrees and deviate it down the second optical rail. The other components that are on here are all set up, not used at the same time. We have a test lens, an aperture with a variable diameter, a microscope objective, and a slit and a photodiode. For the first part of the lab, all we had was an aperture in here, which we closed off as much as possible. Then we translated the microscope to different positions in order to find the Fresnel zones. We looked for a bright spot right in the center, and then a dark spot right in the center, and corresponded until we got a few different Fresnel zones. The next section, we put a test lens in just before the aperture. What we used the aperture for was to stop down the lens even more and change the F number. This lens had about a focal length of about 1 meter. And what we then did was take the objective and put it at the focal point and found a few defocus positions in order to get the proper MTF. So once we found those positions with the objective, we were able to remove the microscope and cut across the beam with a slit and take the voltage measurements with a photo detector and then generate the line spread function.
Now we'll attempt to show you the different Fresnel zones as we translate the microscopic objective down the rail for a circular aperture. This is NF equals 1. This is approximately NF equal 2, where there's a dark spot in the center. This is approximately NF equals 3, where there's a bright spot, a dark ring, and then a bright ring. And then the diffraction pattern gets rapidly more complicated as you move closer to the aperture. Now, here is going to show you the diffraction pattern due to a very large F number lens with a very small aperture. This is about at best focus. As we move back, we see a null fringe, or we see a null spot in the center due to approximately 1 wave of defocus. That's about there. And then as we move through focus the other direction, we can see another spot. By averaging these two positions, we can find best focus. This slide explains a lot of the theory for diffraction from a circular aperture. You can see here how you pass through the different Fresnel zones, and this is the relative irradiance on axis for a long ways down away from the aperture up to very close to the aperture where the Fresnel zones get very close spaced together. The number of Fresnel zones seen is proportional to the aperture radius squared and the distance down the optical rail. This slide explains a lot of the theory behind the modulation transfer function in a diffraction limited system. We wanted to measure the MTF for our lens that we were using in this system, and to do this we went about it by measuring the line spread function, but the MTF is used to figure out the resolution of the system at different spatial frequencies and the contrast at different spatial frequencies.
All right, for our system, we want to design a system that had a spot diameter of 225 microns. In doing so, our diameter of our aperture stop was 6.85 millimeters, which gave us an F number of 146. This is our best focus data, and with this data, we are able to calculate that our spot diameter was actually 180 microns. But we actually took a lot of data points and took it out quite far, and we noticed we could also see diffraction rings beyond that. This fit our profile because as we translated our slit across our solid beam, we get a full peak. And as we move our system, we went to a +2 position. We took our data points again, and we get a dip here in the center. This also fits our data because as we translate our slit, we have a negative or a dark spot in the center. So we have peaks along these edges and a dark spot in the center. So we have that for both our +1 and our +2 and our -2 positions. And this is our data as we put it into MATLAB. This is for our best focus position. The red line indicates our theoretical value, where our cutoff frequency is about 10.8 cycles per millimeter. The blue curve is showing the corrected values, and the green curve showing the uncorrected values. For the n is -2, as we introduce negative waves of defocus, we expect our spatial frequency to decrease, and also for +2, a similar fashion. For our calculations, we calculated the spatial frequency, which is 1 over lambda f number. We input our lens into Zmax with a focal length of 1,000 millimeters. The limiting diameter of the aperture was 6.8 millimeters, so our spatial frequency we calculated was 10.746 line pairs per millimeter. Now, as we calculated our best focus spatial frequency, our MTF shows that the best resolution we're going to have is when we're about 10.82 line pairs per millimeter.